Well, we should start with the problem. A multiple choice one this time. Oh, good. That increases our odds, right? Instead of infinitely many possible answers, there's one of 5 possible. What is the volume for the region described by 0 less than or equal to 2z less than or equal to 3r less than or equal to 6? Now, the blue parts here are basically from the formula sheet. And that's what it looks like on the formula sheet. It's the volume formulas for the sphere, volume formula for a cylinder, volume for a cone. So probably those shapes are involved. And we have some answers. 4 pi, 6 pi, 8 pi, 12 pi, and 24 pi. Does somebody know the answer to this one? Did they work it out? Ah, I see a hand, very enthusiastic.
I don't know if this is right, but is it 8 pi?
Is it 8 pi? Yes, it is 8 pi. Good. All right. That's what I got. So let's figure it out. We'll work it out together. Good. So if you got 8 pi, nice. And if you're wondering how to get there, we'll get there. Now there's a couple of key things here as you read the problem you should pick up on. When you start, you say, I see this word volume. What is volume implying about our type of problem? And in particular, what dimension are we in? 3D. We're in a 3D thing. So we're in 3 dimensions. Okay, so we know we're dealing with 3 dimensions. And then we look at these equations and we start saying, I see things like z and r. What is that telling us? We know we're in 3D. We see z and r. What is that telling us? Cylindrical coordinates. Okay, so we're going to be doing volume, and I'll put 3D, described by cylindrical coordinates. So it doesn't explicitly state it, but we can pick up on things. Now, as you look at these equations, we're in cylindrical coordinates. What don't we see? Theta. Cylindrical coordinates have r, z, and theta. This does not have a theta anywhere. Are we still in cylindrical coordinates if there's no theta? Yes. What does it mean when there's no theta? Yeah, someone said revolution. So this is, essentially it's a volume of revolution. Because what it means, whoops, I can spell revolution. It says, if you think about this in 3D, we talked about how different values of theta corresponded to like half spaces. So you have a half space over here. This would be your theta equals pi halves. And then you have a half space, say, coming off here. This would be your theta equals 0. And you have all sorts of other ones. And the punchline here is whatever shape you see over here, I should have not drawn a weird shape, you'll see the same shape in that slice. It is going to be consistent. So there's some consistency. So how does that help us? Well, what it tells us is to say, you probably just need to understand what's happening in a single cross-section. So it doesn't matter which one we draw. So we'll say, well, just draw them arbitrarily. I like to describe it by z and r. So z, that's this piece going up and down, the z-axis. Then r is just saying what happens as we are coming off the z-axis, regardless of your choice of theta. Okay, so when you have a string of inequalities, don't try to digest it all at once. Break it into easier to understand parts. So let's start with the first inequality. 0 less than or equal to 2z. What is that telling us? What's another way to say 0 is less than or equal to 2z? It says z is positive. Okay, so that tells us we're in this piece of our half space. All right. Well, let me jump ahead and do the last one, 3r less than or equal to 6. What does that become? R is less than or equal to 2. Which tells us that you go over here to r equals 2, and you have to be less than or equal to 2. The last one is probably the most interesting one. That says 2z is less than or equal to 3r. Well, a couple ways to write it, so I'll just say z is less than or equal to 3/2 r. Now, if you had equality, z equals 3/2 r, what are you looking like? Z equals 3/2 r. What if I said y equals 3/2 x? What would you say? Line. So what would you say if you said z equals 3/2 r? Line. Right? These are just symbols. We can change what we call things. So we say, oh, there's this line going up at, z equals 3/2 r. Now, I want z to be less than or equal to 3/2 r. So, am I above the line or below the line? Below! Yeah, exactly. Got it. Good. Because you're less than that. We're below 3/2 r. All right. And now what you do is you take your 3 i's and well, actually, I guess it's hard to do since you only have 2 i's. But imagine you had, and you could overlap. And if you overlap these, you say, well, what's the region where all 3 of these simultaneously hold? What shape are you getting? It's a triangle. You're going to come up to r equals 2. What value of z will you get? 3, because this is 3/2 r. And this is the shape that's common to all 3. Now, what's the volume? Because this is a 2-dimensional thing. What's the volume? Now you turn. Turn, turn, turn. Like the song says. And if you turn, what shape are you going to form? I realized I drew this, but I never utilized it. We're running out of space, but that's okay. We're about to run out of problem. When we think about this, when you spin, what are you going to see? The outer part looks like it's going to be a cylinder, but are we going to have a cylinder? What do we have? We have a cylinder, except we drilled out a cone. So this is a cylinder minus cone. Yes? So how do we find the volume of this shape? We describe the shape as a cylinder minus a cone. So what's the volume? We'll take the volume of the cylinder minus the volume of the cone. Okay, well, we need to answer some questions. For the cylinder, what's our radius? 2. What's our height? 3. And we say, so this is pi 2 squared, because that's our radius, 3. Minus, for our cone, there's a 1/3 pi. Now, what's our radius? 2. It's the same radius. This is still 2. This is our radius up there. So this is 2. All right, so there's still a 2 squared. What's the height? 3. Now here we can get the 3's to cancel. Pi times 4 times 3 makes 12 pi. Pi times 4 is 4 pi, which gives us 8 pi. All right. There you go. Any questions? A nice warm-up problem. And in the last few minutes of class, no. Plenty of time left. Okay. Well, our quote for the day, we'll move to quotes. So, short quote, engage. Famous line from Captain Jean-Luc Picard of the Starship Enterprise. And this was his ways of saying, all right, start the engines. Now, I want to say two things about this, but the first thing is, why do I want to say the word engage? What's going to determine your success in not just this class, but all the classes that you take? It's not your professor. It's not the computer who does the grading or the people who do the grading. It's how much you stay engaged with the material. You'll determine whether you pass or fail this class. I want you to pass. How do you succeed? You stay engaged. You keep coming back to lecture. And thank you for being here. You ask questions, you participate, you take notes, and you're active. You don't let small setbacks hold you back. You keep moving forward, and that will help you succeed. Now, the other thing I want to say, and you're probably of a generation that may not have watched a lot of Star Trek: The Next Generation, but I did. And when they described courses, they would describe it as a pair of numbers. They'd say, okay, laying a course, 2-4, mark 137, engage. It was always a pair of two numbers, 2-4 and 137. What were they representing? They were representing angles. So the first number was essentially saying, okay, relative to the horizontal plane of the ship, which way should I turn? The second number says, okay, how should I come off? In other words, theta and phi. It was spherical coordinates. And that makes sense. So if you were, say, a starship, or maybe you're a plane, bring it a little bit closer to home, you want to describe things relative to yourself. And if I want to describe which way to go, I say I need to say something about that direction, and the easiest way is with a pair of angles. If you're on the ocean, then you just need a single angle, and then you use polar coordinates. But even in the future, you still need to know about spherical coordinates. So good thing we know them now. All right, goals for today. Vectors. And vectors are going to feel somewhat similar to points, but they're different. Vectors are about change. And it's very important when you talk about calculus, how do you talk about change? Because calculus is built on the understanding of how things change. And we'll talk about vectors in both a geometric way and a component way. Component just as a way of saying algebraic. How can we get numbers? Because we love numbers. We're going to talk about how you add and scale vectors. We're going to talk about unit vectors. And we're going to talk about the midpoint. That's a lot to get to, so let's get to it. All right, so as I said, we need change for calculus. So far, we focused on coordinates, which give us location. But we want to say, okay, how am I describing the change between two locations? And this will be what we call vectors. Now, vectors have two important components. So ultimately, when we go to vectors, there will be times when we say, well, we're looking for a vector. Let's break it down into two things we need to know. So one important thing is the amount of change that occurred. And if you're thinking about moving between 2 points, it's the distance between those 2 points. The other thing is the direction of change that occurred. So which way did you go? Now, if you think back to single variable calculus, it said, wait, we didn't have vectors. We used numbers. Well, numbers have built in these two things. You have the magnitude of the number, that's the amount of change, and the direction was where? Plus minus. So you had two directions built in. So those pluses and minuses were acting as direction. And so now, how do we think about it? Well, oftentimes when we draw them visually, we draw them as these line segments with the direction. So we put an arrow on. And so here we have, for example, one vector, here's another vector, and be careful, they're very sharp. Okay, now, keep in mind that when we talk about vectors, it's not the vector that has to be tied to a certain location. We can move the vector. It's still the same vector as long as it represents the same amount of change. So we can move vectors around. So, you know, at the math department special effects budget can do this. Like, what? Wow, that's amazing. Same vector as I move it up and down. Okay, all right, that's our budget for the year. All right. So don't think about it as like, oh, it's tied to a certain location. You can move it wherever it's handy. There's a couple things you want to do. Well, there's a lot of things you want to do, but we'll start with two. Scaling a vector. Scaling a vector says, I want to change its length. So I can make it twice as long. I can make it half as long. If you scale by a negative, it also says, oh, and then just go in the opposite direction. So putting a minus in front just says, go backwards. And there's a word that we'll see, which is parallel. And I like to think of parallel says, they're going in the same way. More technically correct is two vectors are parallel if you can scale one and you get the other. That's what we mean by parallel. So they only differ by scaling. Now, the other thing is we can have multiple vectors, and we say, well, let's add vectors. So we say, okay, what does a vector represent? It represents change. So if I have two vectors, and I want to say, well, what's the combined change? I'll just link them. So I have a vector u and a vector w. And by the way, you'll notice we put these little arrows on top. That's one of the ways that you'll sometimes see a vector written. Another way you'll see a vector written is if you see a very bold letter. So if you it's not just a V, it's like V, it's like bolded V, right? That's a vector notation. So if I want to know what's the combined change of u and w, say, okay, just take w and move it so where it starts is where u ends. So it's first u and then w, and you say, okay, the net change is the same as just going straight from the start of u to now where is the end of w. So that's u plus w. So you can add vectors by chaining them together. All right, so that's some very basic things. That's thinking more in the lines of the geometric ideas. Any questions so far? Yes?
When you said that the vectors differ by scale, can you explain how they're parallel again?
So if you think about, so here's v and 2v, and they're moving, the directions are the same, right? Because vectors have direction and amount of change. So when I double it, what have I changed? Well, I've just made this one longer, twice as long. So parallel, I like to think of as they're going on like parallel train tracks, right? They're just moving in the same direction. They're just changing by a different amount. And so we say they're parallel if they have common direction. Again, direction is a little bit misleading because you have the notion you could multiply by a negative. All right. Numbers. All right, I know we want numbers. So we're going to start with three very special vectors. We'll call them I, j, and k. On a side note, you probably have picked this up, but mathematicians have sort of carved up the alphabet. And they said, we're going to let the x, y, and z be variables. We'll let a, b, and c represent constants. And so I, j, and k, that's the part of the alphabet, that's the vector part. F, G, and H, that's their function part. We're running out of real estate really quickly. So what are I, j, and k? They're unit vectors, and it just means a vector with length 1. We'll talk more about unit vectors in a few minutes. Vectors of length 1, pointing in very convenient directions. I points in the direction of the positive x-axis. J points in the direction of the positive y-axis. K in the direction of the positive z-axis. And that's what they are. Okay, great. But every point we've described in terms of x, y, and z, so this feels like we're onto something here. And we have this convenient fact. Every vector can be rewritten as a combination of I, j, k. So when I talk about a combination of I, j, k, some scaling factor times I plus some scaling factor times j plus some scaling factor times k. How do we do it? Well, suppose we're at a point. And that's the start of our vector, and we go to the end of the vector. So I'm going from x1, y1, z1, all the way over to x2, y2, z2. Now, what can we do is instead of one vector here, which is the vector v, we'll break it up into 3 vectors that do the following. The first part only moves in the x direction. The second part only in the y direction. And the third part only in the z direction. But I'm going to end up at the same location. So I have 3 vectors that do the same effect as this one single vector. Well, what's the advantage? Well, what happens is now we can figure out this vector moves in the I direction, so it's parallel to I. It's some multiple of I. Well, how much is that multiple? And the answer is, well, look at how much you changed in x. So it's x2 minus x1 times I. This vector, it's parallel to y, which means it moves in the y direction, so it's parallel to j. So it's some multiple of j, because if we're moving in the same direction, we differ by scaling. How much? It's the change in the y coordinates. And similarly, the z. So if I want to know what's the vector that goes between them, I just take the difference in x times I, difference in y times j, and difference in z times k. This is also written as a list of 3 numbers where we use angled brackets. So these are not parentheses, they're angled. And that helps us distinguish from numbers. I will let you know that you will see the ijk notation and you will see the angled bracket notation. They mean the same thing. We're breaking up our vector according to the changes in the different directions. So both notations here are used. Okay, so now vectors, there's not so hard to find. If I know where I start, I know where I stop, just take the differences in each entry. Well, we talked about scaling. We talked about adding. Turns out, when you write it in this component form, it's still very straightforward. If you want to scale every entry. So in other words, if I have some multiple k times the vector a, b, c, well, this k is acting as the scaling factor. So I'm scaling the vector a, b, c by k. So this is k times a, k times b, k times c. If I want to add 2 vectors together, add the corresponding entries together. Because, what's going on? If I want to know my total change in x, I say, what's my change in x from the first? What's my change in x from the second? Add them together, that's my total change in x. So vectors work very, very conveniently. Very conveniently. And at this point, you're like, cool. Why didn't we do this with points? Well, with vectors, adding vectors and scaling vectors is great. It makes sense. Adding points, adding locations, and scaling locations doesn't work. It doesn't work. The reason I say it doesn't work is the underlying geometry is conditional based upon how you're describing it. We don't want that. So that's why there's a fundamental flaw. So be careful. You can do things with vectors you can't do with points. So there are advantages to vectors. All right, good. Well, a few more things. We need to know 2 things about a vector: the length of the vector, the direction of the vector. So let's talk about the magnitude. So the magnitude of a vector, we denote it by putting what looks like absolute value signs. But a better way to think of absolute value signs is to say, these tell us something about size. So it's like a size thing. So it's trying to say, hey, what's the size of your vector? And so how do we measure it? What's the length? Well, geometrically, no problem. Just pull out your ruler and say, okay, it's 3.5 inches. All right, great. But we usually don't work with that. We have to have something that's a little bit better. So you say, okay, what about component form? You have a list of numbers. What do you do? Well, what you can do is use the distance formula. So what I like to think of doing is to say, well, our vector can be anywhere. So let's make it in a convenient location. And one convenient location is to put the tail of the vector at 0, 0, 0. And then I have this vector, which is A, B, C. Where will this point be? So if I start at 0, 0, 0, I change A, B, and C respectively. Where do I end up? A, B, C. I can say how much I changed in each coordinate, and that helps me find my new location. So now the length of the vector ABC is the distance from the tail, which is where you start, and the head of the vector. So use the distance formula, square root of A squared plus B squared plus C squared. All right. So that's our length. We can find length of vectors. For directions, we're going to turn to what are called unit vectors. Now, have we seen the word unit before in math? Any famous example? Unit circle. Yeah, in trigonometry. What's a unit circle? Circle of radius 1. But this shows up in other places, like in our language. We see things like unicycle, one wheel. Unibrow, one eyebrow. Unicorn, when there's only one piece of corn left at the dinner table. These all show up. So when you see the word una, you think 1. All right, so we have vectors with length 1. That's the clue. Well, now if we say, look, the length of the vector is 1, then the only thing that matters is the direction, because I automatically know the length. And since there's 2 parts, length and direction, that says the only thing that matters about that vector is direction. So we use unit vectors to represent direction. Now there is a little caveat. There's something called the zero vector. And the zero vector in component forms, 0, 0, 0, that's the vector. It has no magnitude. And it has no direction at all. I like to call it the art history major of directions. It's not going anywhere, right? Okay. So, don't worry, there are no art history majors on campus except my dean. But he never listens to my lecture, so I'm safe. All right. So, this vector is special and has no direction. Any other vector that's not 0, you can make into a unit vector by saying, let's fix the length. How do you fix the length? You say, well, I just need to scale by an appropriate amount so that the length is just right. So, what you do is take your vector and scale it by 1 over the magnitude. So if your vector had length 2, scale by 1/2. If your vector had a length 1/3, scale by 3. Just whatever you need so that it has the right length. All right, so that's a lot of stuff about vectors. Drinking from the fire hose. How are you doing? Drinking from the fire hose. You've never heard that expression? Oh, I'm getting old. It's when you... So a fire hose... There's like a normal hose. It's like a little bit of water. A fire hose, is a lot of water. And so it's really hard to drink from the fire hose because there's too much water. Too much to consume all at once. All right. So, with all of that said, here's a problem. Find all values of t so that the vector, which looks like 2, negative 1, 1, plus t, negative 4, 1, negative 2, is a unit vector. So notice that every choice of t produces a vector. Because what it does is that the t scales the second one, then you can combine the two together. And we want to find all the values. And by the way, all might include that there are no such values. That can happen. But all the values of t so that we can produce a unit vector. Anyone find one answer? Yes? Negative 5/7 and negative 1/3? Oh, that's really close to what I got. We'll compare our answers in a second. Anyone else? All right. All right. So let's take a look really quick. Now, first off, how do you know something's a unit vector?
It says it.
You know it's a unit vector because it says it? Oh, that's a bold way. But 1, right? So we want to have the length equal 1. But length is annoying because length has what? Square root! We don't want to deal with square root, so what can we do? Square it. So we want the length squared to be 1. All right, now we say, well, but wait, Steve, hold on. We can't just square that yet because we need to put that as one vector. Okay, so let's put it as a vector. So as a single vector, what would the first entry look like? 2 minus 4t. The second entry? Negative 1 and plus t, or t minus 1. The last entry? 1 minus 2t. So we need to have this squared equal 1. Well, to take the square, you just square the individual entries and add. So 2 minus 4 squared plus negative 1 plus t squared plus 1 minus 2t squared equals 1. Now, at this point, it's a pure algebra problem. Everything past here is algebra. 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 Ah, what a beautiful thing. Okay, so 4 minus 16t plus 16t squared plus 1 minus 2t plus t squared plus 1 minus 4t plus 4t squared. If you're worried, is this the kind of algebra we put on an exam? Probably not. I don't think so. We're much nicer than we used to be. But we do things like we have some 1s. We can cancel a 1 with a 1 on the other side. The t squareds, well, we have a 16t squared, a t squared, and a 4t squared. Their powers combined, they are 21t squared. And then we say, okay, what else do we have? Well, we have a minus 16t, minus 2t, minus 4t. And if we put those together, what do we have? That's going to be minus 22t, I believe. And then we have the constants. And we canceled one of them. So that leaves us with a plus 5. So 21t squared minus 22t plus 5 equals 0. And now you can do the quadratic formula. Or this does factor as 3t minus 1 times 7t minus 5. I do not claim that factoring is this quick, but in the interest of time, you can check. 21t squared. Here's minus 15t minus 7t. That's minus 22t. And there's a plus 5. Giving us, well, when does 3t minus 1 equal 0? 1/3. When does 7t minus 5 equal 0? 5/7. And those are the two possible times. So you were very close. I think it was just a sign thing. So nice. Good job. don't stress if you're like, this is algebra. If you got to here, awesome job. All right? Now, we still have time. We have minutes left, like 5. So I know you're like, this sounded like a great denouement. No. The fun continues. Okay, because there's other things we haven't mentioned yet. All right, so what haven't we mentioned about today? We haven't talked about midpoints. Now, you might say, well, what's a midpoint? Well, it's a point that's mid. No. Mid means halfway. You're halfway in between. And so, if I have a point x1, y1, z1, and a point x2, y2, z2, I can imagine a line segment connecting those 2 points. And I say, okay, I have a line segment. I can find the middle point of that line segment. That's the midpoint. But I can find the coordinates. And I find it by taking x1 plus x2 over 2, y1 plus y2 over 2, and z1 plus z2 over 2. In other words, I average the coordinates. Now, it feels like we added the 2 points together and divide by 2, because that seems like we're taking the average. And yeah, that's kind of what we did. But we didn't technically do that, because you can't add points. Why is this here in the vector part? Well, you can imagine doing an example. Let's suppose we have 0, 7, 2. Over here you have 4, 1, and 6. What you can say is, well, let's find a vector. What's the vector that goes from 0, 7, 2 to 4, 1, 6? You should be able to read that off. Take the differences. 4, negative 6, because we went down by 6, 1, subtract 7, and 4. Now, if I want to go halfway, what's the vector that goes halfway? Yeah, I scale by half. So 1/2 of this 4, negative 6, 4 is 2, negative 3, 2. And you say, okay, if I know where I start here, and I know how I change, I know where I end. So which point do we end at? 2, because start at 0, change by 2. 4, start at 7, change by minus 3. And 4. And that's the midpoint. If you work through that in generality, that's the formula you get. So it's the vectors can help justify the argument. Now, in the last minute and a half, we won't do this whole problem, but I want to just talk about the idea. Find the point P which is furthest from the point negative 8, 2, 4, and lies on the sphere x minus 2 squared plus y minus 7 squared plus z plus 6 squared equals 36. So it's 2, 7, negative 6, and it has a radius of 6. All right, now, at this point you're like, cool, what does this have to do with vectors? Well, think of the picture. If I want the point which is furthest from this point, but on the sphere, go through the center of the sphere and see where you hit the other side. That's going to be the point you want. That's our desired point. But there's a catch. How do we find it? Well, what's a vector that you do know? We can go from point to center. We can find this vector. And indeed, if you write it down, you change by 10, then by 5, and then by negative 10. Now, very conveniently, you can scale out a 5. There's this pro tip. I hope you notice these. These are useful pieces of advice. You can scale. What's a more convenient vector for us to work with if all we care about is direction? 2, 1, negative 2. Now, here's the thing. This is going in the right direction. What's the part that we need to do? Well, we just have to go that same direction, but distance 6. On a side note, does anybody recognize the magnitude of this vector? 3. So how much further do we have to go? 2 more copies of this vector. So we need to go 4 to negative 4. Because if I have a vector of length 3 and I double it, I have a vector of length 6. Now, that's not the answer. That's how much I have to change by. So what is the answer? 6, 9, negative 10. Oh, I guess we will do the problem.